and welcome to Saturday's edition of Cracking the Cryptic, where we have moved from yesterday's puzzle, in which basically I was given no information at all, to today's puzzle by Marvin Canhauser, in which I'm given loads of information. This must be one of the busiest grids we've had on Cracking the Cryptic recently. Look, I've got cages, Kropki dots, a diagonal, some quadruples, some X's, all sorts of, and arrows as well. Wow, and an even square, presumably. Is that an even square? Well, we'll get to the rules in a minute and we'll work it out, but yeah, lots of stuff going on in this grid, and apparently this is it's called medley, and that's presumably because we've got such a lot of busy information, and the testing reports say that this is a rather lovely puzzle. So yeah, we should be in for a treat as always. I need to interrupt myself quickly. I need to interrupt myself and tell you about a bonus video that's available at the moment on Patreon. It's free, it's not behind the paywall, so you can simply go to our Patreon page and you'll be able to find a video that talks about last night's solve of Roman Whispers by PHISTOMEFEL. This is an extraordinary puzzle. It's ridiculously clever. And my video was about an hour and a half, was it? Making my way through the logic. But after about 50 minutes of solving this yesterday, there is a flaw in my logic, and it related to this little Whispers arrow, which I managed to prove had a 9 on it. And then I did exactly what I did at a different point in the video, but I managed to catch myself the other time I made this error. Sometimes I get the causality in my brain mixed up. So when I saw the 9 on this, I thought, aha, it must have a 4 on it. Of course, the logic works the other way around. If there's a 4 on it, there has to be a 9 on it. But if there's a 9 on it, there doesn't have to be a 4 on it. And I needed to close that gap. I felt I owed it to you, especially because some of the logic to close that gap is so beautiful. I mean, it's unbelievable what PHISTOMEFEL has built into this. Anyway, so I've done that, and I recorded a video about that late last night. Then I got an email from PHISTOMEFEL himself in the small hours. I'd emailed him to apologise for making this error. And PHISTOMEFEL wrote back to say, don't worry about it, but also to say that I could have thought about the break-in slightly differently. And he explained how I could have and should have perhaps thought about it. So I wanted to share those bits of logic with you as well, because they're fascinating and they do make it a bit less bifurcated than I feel my solve was. So there's a 15-minute video, as I say. It's available right now. I commend it to you. It's a bit of a mea culpa, and I'm really sorry that that my brain wasn't switched on enough to catch the error real time, but it wasn't. And yeah, anyway, so that's there for you guys right now over there. The only thing I've got to remind you about today is if you're a patron of the channel, do check out our Quite Approachable Sudoku Hunt, which is available right now. It came out on the 1st of February. We're closing in on 1,000 correct entries already, which is an extraordinary number. And the feedback's been great. It has been great. It's clearly, I think, you have all welcomed something a little bit easier than some of the hunts we've had in recent times. So do check that out. If you want some light relief and a bit of doable Sudoku, then that should certainly be up your street. Now, that's all I've got to tell you, so we might as well get on with medley, and I'll read you the rules. They're as follows. So we've got normal Sudoku rules apply. Digits in cages add up to the small number in the corner if given. Okay, so we've got 2 cages that have to add up to 12 there, so that could be, I don't know, 5 and 7, for example. They add up to 12. This one is a 9-cell cage, and that's, well, the next part of the instructions is that digits cannot repeat within a cage, so we actually know what the sum of this cage is, even though there is no clue. And I'll get on to how we know that when I actually try and solve the puzzle. The main diagonal in blue must include the digits 1 to 9 once each. So this diagonal has a set of the digits 1 to 9 on it. Digits within the white circles must appear at least once in the 4 surrounding cells. Right, so that's telling us that these cells here have to include the digits 6, 7 and 8. these digits have to include the digits 2, 7 and 8, but in this case I suppose they could include 2 of them, because you could do something like that and not break the rules of Sudoku. So yeah, we just have to make sure there's at least one of the digits in the circle in the cells that the circle touches. Digits on arrows sum to the digit in that arrow circle, so that's telling us that those 2 digits there, let's make that 2 and that 7. 2 plus 7 equals 9, so that would be a legitimate way of filling this arrow, although it might break the crop key dot, I'm just seeing. What else have we got? We have got the 2 digits on the two-cell palindrome must be the same. Okay, so those 2 cells, well, yeah, okay, this is a palindrome, which means it reads the same backwards and forwards. The effect of that is to make those digits the same digit. So those 2 digits are the same. The cell with the grey square must be an even digit, that's what we thought, so that's even. Cells separated by an X must contain digits that sum to 10. We've got everything going on in this one. So that could be 2 and 8, for example. That would be a legitimate way of filling this domino. Just make sure the domino sums to 10. Black dots separate cells connecting digits. Black dots, hang on, separate cells containing digits with a ratio of 1 to 2. Yeah, that makes sense. So this domino, we have to make sure one of the cells is double the other one. So we could have a 2 here and a 4 here, for example. That would be a legitimate way of filling a black dot. And white dots separate cells containing consecutive digits. So let's look at this one, which is on the arrow as well. That could be a 3 and that could be a 4. But it could also be a 2. We just have to make sure the domino is consecutive, and obviously that's then going to impact on the arrow as well, or the circle. So do have a go at this. A lot of rules, but I think all of them are totally standard, so it shouldn't be anything too complicated if you're used to variant Sudoku. The way to play? Well, it's to click the link under the video as usual, and now I get to play. Let's get cracking. And okay, so where shall we start with this puzzle? I love quadruple puzzles, by the way. We don't do nearly enough of them. I can't remember the last time I did a puzzle that had a quadruple clue in it. So, okay, well, one thing I can see, which is very minor, is that those 6 digits are all different digits. So the other digits, so what that means is that these 7 cells have to contain the digits 2, 4, 6, 7, 8 and 9 in box 1. That means the other 2 cells have to contain the digits that are not in those circles. So these digits have to be 1, 3 or 5. Now, I'm not sure about that one. This one's a bit more complicated because literally it sees 4 different boxes of the Sudoku. And we don't even know if the 2 that's got to be in that quadruple overlaps with the 2 that lives in this quadruple. It doesn't have to. So we don't have to make this cell a 2. That could be a 2, and then that could be a 2. That would be completely fine. That would put a 2 there, and an 8 here. It would mean that this wasn't 4, 8. Right, so what do we do to start this puzzle? We shall... I might be able to do... Oh, let me get to the maths. I was about to try and do maths on this box, but I've remembered I was meant to do maths on this 9-cell cage, wasn't I? Because you can't repeat a digit in the cage, there is a secret that exists in this cage, and I only let my favourite people know the secret, but that's fine because you're one of those people. So because the digits 1 to 9 must appear once each in this cage because there can't be a repeated digit, we know that the sum of this cage is the sum of the digits 1 to 9. If you add the digits 1 to 9, you get 45. So this cage could have had a 45 clue in its top left corner, but Marvin was very unkind and didn't give us that. But that rule of 45 obviously applies to a box of the Sudoku as well. So that box must sum to 45. Now we've got a 12 cage plus 10 there and 10 there, so that's 32. That means these 3 cells have got to add up to 13 to make sure the box overall adds to 45. And 13 in 3 cells I don't think is very restricted. We've got a black dot on an arrow here. Right, okay, we can do some mathematics on this circle. Because if we think about the nature of a black dot, we could represent it algebraically as one of these cells is x, and the other cell would then have to be 2x. So this, what's the sum of this arrow? Well, it's 3x. So this must be a multiple of 3. Therefore, it must be 3, 6, or 9. And that means this must either be 1, 2, 2, 4, or 3, 6, which basically means it's got lots of options. That cell is obviously 2, 4, 6, or 8. We're getting a bit pencil marky about this. This arrow has a consecutive dot on it. So what we can say about this cell is it must be odd, because any consecutive domino will contain an odd and an even digit. And if you add an odd and an even digit together, you'll get an odd digit. So this square must be 1, 3, 5, 7, or 9. It can't be 1, because we can't make this 1 and 0. So this is a 3, 5, 7, or 9. I don't actually see. I'm not doing very well at this so far. Okay. We know the 2 cells on the palindrome are the same. So in box 5, they live in one of those 4 cells. Oh no, the diagonal isn't actually impacted by that at all. Ah, right, that is interesting. Right, let's just highlight these cells for a moment and ask where this digit, which we know exists in the 2 red squares, where does it go in the 9-cell cage? Because it must exist in the 9-cell cage. And you can see, if you look carefully, it can't go in those squares, because then it would repeat in box 6. It can't go in these squares, because then it would repeat in box 8. And it can't go in either of those 2 squares, because they see the red squares by Sudoku. So it's got to go here. That is red. Which means red is up there somewhere, and red is over here somewhere. Now, that's very, very annoying indeed. I thought we might get some traction there, but we don't, because, well, we can't even conclude it's possible that that's red and that's red. Or it's possible that that's red and one of those is red. If that was a 6, that could be a 4-6 pair. Wow, okay, that doesn't seem to do anything, does it? So if that's... Or maybe a better question is, where does that go? Where does this cell go in box 8? Because it can't be on its own arrow. So it's ruled out of those 5 cells. So this digit here, whatever that is, give it a purple marking, can't go in those cells. It could be in the red cell, and then it would sort of proliferate around the grid. Or it's in the cage. Now if it's in the cage, here, it can't be in the cage here. So it would be in one of those 3 cells. Okay, so the other way of thinking about this is to say, where does this cell go in box 9? And the answer is not in those cells and not in those 2 cells either. And the reason it doesn't go in either of these cells is because it's because of what happens in box 8, where purple is either the red digit, in which case the only place it goes in the cage is here, or it's in the cage, in which case it can't go in those 2 squares. So its only option, if it's going to be in the cage in box 9, is the red cell. So these cells and these cells can't be purple. But that still leaves 4 possibilities for purple, 2 of which would work on the black dot anyway. Oh dear, I am not understanding this at all, am I? This is abysmal. Come on, Simon. I've got 2 black dots in a row here, but these aren't. Sometimes if you get black dots that are connected, like if there was a black dot here, you could put a 2 or a 4 in the middle cell. Here we know no such thing. Can we... I'm wondering whether this 12 cage is... Are all options really possible for this 12 cage? Because it's either 5, 7, 4, 8 or 3, 9. If it's 3, 9, this becomes a 6. 3, 9, 6. No, that doesn't work. Right, this is not 3, 9. Because if that's 3, 9 and this is 6, there are not enough ways to fill the 10 cages anymore. Because you can see 3, 7, 1, 9 and 4, 6 would be unavailable. So the only option left would be 2, 8, and we couldn't repeat that in both dominoes. So this 12 cage is 5, 7 or 4, 8. Now let's see if we can do that again. If this is 4, 8, the 10 cages would have to be odd digits, so they would be 1, 9 and 3, 7, and this would be a 6. And that would have to be 2, 5, and that might be okay actually. Okay, so that was 4, 8, wasn't it? 5, 7 is not going to put as much pressure on the 10 cages because obviously you're only removing one of the options, which is the 3, 7 option. 5 can never be on a domino with an X because that would just make it double 5. So I don't know that we can do better than that. Good grief. Okay. So what on earth is it we're meant to do here? Can we do some geometry somehow? I don't like the look of geometry. Be very unusual as well to put geometry into a puzzle this busy, I think. So if we were going to try geometry, we'd have to put the arrows in a different set of digits to their circles. Oh, my phone is going nuts. So what are we looking at there? We're looking at some sort of relationship between column 9 and row 9, and maybe box 8 and box 6. Let's have a quick look at that. So if we make those yellow, that would be double counted, and make these green. That's not going to be visible. Make it blue. That's quite visible. Okay, so this way we could cancel out everything that has a blue and a yellow flash. No, hang on a minute. If I add that as well as blue, and then I add that as well as yellow, I'm getting all sorts of cancelling done. Yeah, okay, let's stop there and let's actually analyse what I'm doing. So I'm wondering whether we can use set equivalence theory to make any progress here. So the way we would need to do that is to think about the yellow cells. So what is the nature of row 9 of this grid? What digits are we expecting there to be in row 9? Well, row 9 will contain a set of the digits 1 to 9 once each. So this is a set of the digits 1 to 9. Column 9 is the same. That is another set of the digits 1 to 9. So I want to imagine that we write down on a Scrabble tile each of the digits 1 to 9, and we do it twice because we've got one row there and one column there. So 18 Scrabble tiles, and on those Scrabble tiles there will be 2-digit 1s, 2-digit 2s, 2-digit 3s, etc. all the way up to digit 9. Then I want to do the same thing with some blue Scrabble tiles. So I'm going to put my yellow Scrabble tiles in a bag, a yellow bag, they're in this yellow bag. Do the same with some blue Scrabble tiles. So again, I'm going to have 18 Scrabble tiles representing the blue cells, And those Scrabble tiles are going to contain 2-digit 1s, 2-digit 2s, etc., all the way up to 2-digit 9s. Now, this is where it gets interesting. I think we might have to remember that this cell here, whatever that digit is, that's in the yellow Scrabble tiles bag twice, because it was in column 9 and it's in row 9. So that's in twice. We'll make that, I'll give it a, oh no, purple I've already used. I'll give it a black flash just for the moment. Now, what I want to do now is put some more tiles into both bags. So into my blue bag, I'm actually going to add those digits as well. That's another set of the digits 1 to 9. So 9 more Scrabble tiles in blue, and one each of the digits 1 to 9. And then I'm going to put one more set to equalize the bags and make sure they contain the same number of Scrabble tiles with exactly the same digits on them. I'm going to add that set of the digits 1 to 9, those tiles, into my yellow bag. So now I've got 27 tiles in yellow, 27 tiles in blue, and then I'm going to go about the business of throwing tiles out of both bags. So any digit or any if we examine this cell, we've no idea what's in that cell, but we know it appears. That tile appears both in the yellow bag and in the blue bag. So if I rummage around and find that tile, I can throw it out of both bags, and it will still be true to say that what remains in the bags, the 26 remaining tiles in yellow and the 26 remaining tiles in blue, must still be the identical set of digits, because they were identical before I removed the same thing from both bags. And we can do that for any cell that has 2 colours in it. So all of these, look, can just be thrown away from both bags. Now this one is more complicated, because remember this cell here is in the yellow bag twice, and it's only in the blue bag once. So I can rummage around and find it in the blue bag and throw it away from there, but I can only throw it once out of the yellow bag to make sure that I'm taking the same thing out of both bags. So in fact, this digit here will remain once as a yellow. Whatever that cell contains is still in the yellow bag once. Now, the whole genesis for this idea was thinking about using the arrows to sort of equalize things. And now you can see, well, let's stop here actually. We can say at this point that the yellow digits are exactly the same digits as the blue digits. And if we count them, we should find that we've got the same number. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Yes, so they're the same number of digits, and they are the same digits somehow arranged. If we add up those digits, because we know they're the same, we know they add up to the same number. So now I want to switch from saying that the digits are the same to saying their sums are the same. Because of the rules of arrow Sudoku, I know that those 2 tiles there, if I was to remove these 2 tiles from the blue bag and this tile specifically from the yellow bag, then the sum of both bags would still be the same, even though the tiles in the bags would be now different, because I would have a different number of blue tiles left compared to my yellow bag. So I'm going to do that. I'm going to remove those tiles from my blue bag, and as compensation I can take this one out of yellow, and I'm going to do the same with this arrow. So I'm going to take those out. And now, well, now it's actually very interesting, because now at the end of all this, we have proved that we've got yellow tiles that sum to 20 plus that digit, which is even. So the yellow tiles sum to either 22, 24, 26 or 28, and they sum up to those 3 blue squares, and that digit we don't know, but that digit's repeated. Oh, that was the digit that had to go there, so we can restore the red tiling now. Oh, and I think the red tiling could go in those squares as well. So, right, so the set is just relating to the yellow tiles, though. In fact, maybe I'll remove the red tiling. I think that's getting a bit complicated, sorry. I will just do that, because I don't want this to be overly complicated. So now I've got 20 something in yellow, and in blue I've got that same number. So this digit must be even, mustn't it? Because those two digits are repeated, so they can be represented as 2x. They add up to an even number. So this must be an even number because we know the yellow digits are even. So that's 2, 4, 6, or 8. And we know that the sum of the yellow digits is at least 22. If that was a 2, which is the least it could be, we'd have to put 22. So that can never be a 2, because the most I could make those would be double 9. Double 9 plus 2 is only 20, so that's not going to work. So this square is now 4, 6, or 8. And double 9 is fine. Double 8 is fine. Double 7 is 14. And we've got to get to at least 20. No, double 7 is okay. Double 6 might. No, double 6 is not enough. If we double 6 the palindrome, that would be 12 plus a maximum of 8, which is 20, and that's not the same as 22. So those two digits are 7, 8, or 9, and therefore this digit is 7, 8, or 9. It definitely feels like progress, but it still actually doesn't seem to do anything. So can that be an 8 then? No, okay, no, of course it can't. That can't be an 8, because that would mean these cells had to average higher than 9, and no matter how much pressure we put on them and how much we bribe them or coerce them, that will not work. So that square there has got to be no higher than, is 6 even possible? If it's 26, double 9, 8, yeah, that would work. Okay, so 2, 4, 6. So if either of the x's were 4, 6, this would have to be a 2, and then these would have to sum to 22. If that's double 7, you get 7 here. That would have to be 8. 2, 7. Ooh. Right. Okay. So maybe. Wow. Okay. I wanted to just have a look at this. I think we can show this is not 7. I'm now wondering if we use the quadruples. Maybe all of these quadruples are important now. Because if we double 7, the palindrome, that's a 7. And now to make this a high enough total, we have to put an 8 here. And to make this yellow small enough, we have to put a 2 here. And we get a 2, 7, 8 triple on the diagonal, which breaks this quadruple. Because now I couldn't put 2, 7, or 8 in either of those squares, and I can't put 3 digits in those two squares. That's really beautiful. That's really quality. So now I want to try 8 here. So if these are 8, this is 8. Now, that can't be 8 now, so that has to be 6, because if it's 8, 8, 4, it only adds up to 20. So again we get a 2 here. And we get 2, 6, 8. No, that doesn't quite fit. 2, 6, 8 puts... Oh wow! No! This is still very beautiful. Okay, if this is 2, 6, 8, that that quadruple, it's the 6 and 8 on it have to go in those two squares, and now that means that there's a 7 in one of these two squares, which reflects back on this one. Well, the way to think about it is that because there's a 7 in one of those squares, and there's a 8 and a 2 in these squares. Again, we get the same problem. I've got to put the digits 2, 7 and 8 into those two squares again. That won't work. It's impossible. So I think we've got a digit. We've got a digit. Because now we can say, let's go back to here, that these have to be 9s. And therefore this has to be 9. And therefore 9 in that quadruple has to be off the diagonal. So now we've got 18 plus this digit. So this is at least 22. Okay, so now this digit is always 2 less than this digit. So these are in the ratio. Well, they're not in a ratio, they're in a relationship. And the relationship keeps them 2 apart, with this being the lower number. Oh, bobbins, I was just wondering whether we could use the 9s there. And we can't. We already ruled a 9 out from here. We ruled 3 9 out from there at the start by looking at this square. We can, though, now rule 9 out from this 12 cage. So that 12 cage is 4 8 or 5 7. So do we know whether these are different now? If this was 4 8 and this was 4 8, that would have to be 8. And that would have to be 2 4 9. I'm not sure I like that. Hang on, let me just think about this. If these are the same, the digit that they have in common, which is either going to, the high digit they have in common, which is either 7 or 8, has to go here. Neither of which is allowed in the they're both allowed in the 2 4 9 quadruple clue, but that would make these squares have to be 2 4 9. These squares are 2 4 9. This is 7 or 8. Something's nagging at me here. But I don't see why it's broken. I have a feeling that's broken, I just can't see why. Sorry, my brain isn't working there. If it is broken, apologies. It looks, as I say, I can't rationalise it, but it doesn't feel like it should work. As I'm staring at it, I now can't see why it can't work. So maybe they can be the same. Right. So what does this mean? We've got 9s here. We've got this digit is 2 less than this digit. Oh, I tell you what we can't do. We can't have 2 here and 4 here, because that's going to break that quadruple. This puzzle's really it's really unusual the way it works. To have so much given information and then need set to break it open, and then to use the diagonal with the quadruple clues. It's really cool, because if this was a 2-4 pair, that quadruple clue now needs to have 3 digits in those 2 squares, which again won't work. So we can just get rid of 2 from that. So that's not 2, that's not 4. So this is either 4 6 or 6 8. So it's always got 6 on it, which means there's always a 6 now in one of those 2 cells. Oh, and that means that Kropki dot can't be 3 6 anymore. So this Kropki dot here is now either 1 2 2 4 or 4 8. Oh, that's rather beautiful actually. It's not 4 8, because if it's 4 8, what do you put into those 2 squares? And the answer is both of them have to be 6, which won't work. So this is not 4 8, so it's not got an 8 on it, so it must have a 2 on it. This is either 1 2 or 2 4, so that square is not 2 anymore. 2 must be on an X. Oh yeah, this is so lovely. Good grief. Yeah, Sudoku now. 2 has to be in one of, 2 is in this domino, whether it's a 1 2 or a 2 4. So the 2 in box 7 has to be on an X, where it will be a 2 8 pair, and therefore you can't put 4 8 in the 12 cage. So this is 5 7. And now you can't put 3 on an X. Right, okay. Is that interesting? Let me just think about this. can't put 3 on an X. Because obviously 3 needs a 7. I've got to put 2 on an X. So one of these is 2, 8. Don't know. I can't quite see what that's doing. If get rid of 2 from here, it doesn't prevent this. Does it prevent that from being 4? If this is 4, this needs to be 2 or 8, and it can be neither. Yes, it does. Okay, so this is down to 1, 2, 3, or 6. Two, 3, 4. So if the part, yeah, okay, maybe we've got to think about this domino still. If this is 2, 4, you have to put 4 and 6 on the X's. But if this is 1, 2, you have to put 1, 9 on the X's as well as the 2, 8 on the X's. 4, 6. I'm wondering if that somehow means this has to be a 3. Not sure, sorry. Okay, where on earth do we look now then? I thought we were going to break into it there, but I can't see how to do it. So we're going to have to think again. Where shall we look? We shall look at... I have no idea. I have no idea. We shall look at... Let's have a think about this one then. Yeah, okay. This is a consecutive sequence of dots. So we can't put sort of a big and a little digit in there to add up to 9. If this is a 9, that has to be 4, 5. So that tells us that these digits are always 1s, 2s, 3s, 4s, or 5s. Now, oh no, I was about to say that's interesting for that digit, but if that digit's 4, it can go on the dot. If this is a 6, it has to go in here. And then oh, that would be massive. Good grief. If that digit's a 6, look at the way the geometry works. It forces a 6 into the cage here. Therefore, you can't repeat it there. And because it would be here, it can't be there. And it would be forced onto the black dot. So if that's a 6, that's a 9. And that... oh, that doesn't work. That doesn't work. Okay, that's weird. If that's a 6, you've got to put 6 in here. Oh no, it does work. It does work. It just forces that to be 3, 6 and that to be 9. Okay, I was suddenly getting confused about whether I could put a 6 in the box. I can, it just has to be on the black dot. So 3, 6, 9 here is okay. But 9 has to be in one of those 3 cells by Sudoku. That was the red highlighting we did earlier, which I of course abandoned during our set analysis. Oh, 5, 7. That can't be a 5. So have we got this? No. Okay, I was just wondering if we could do the same sort of thing up here. Although there is some symmetry around this diagonal, it's very far from perfect, isn't there? There's sort of these which would be symmetrically equivalent. The 12s would be symmetrically equivalent. This is symmetrically equivalent, but the actual disposal of the dots is very much not symmetrically equivalent. Okay. We do some Sudoku. Where does that digit go in row 7? That digit there can't go in those 2 squares. It also doesn't seem to be able to go in any of the other squares, so it goes there. So that digit and that digit are the same digit. They are 5s or 7s. Aha! Right, okay, well now I can tell you this is not a 3. Because if that's a 3, Where do you put 3 in row 7? Answer, nowhere. It won't go anywhere. If that's a 3, you can't put 3 here, because then this would have to be a 0. So 3 would be ruled out of those 3 squares. It doesn't seem to be able to go in any of the others. So that is not a 3. So this is not a 1-2 pair anymore. So it's not got a 1 on it. If that's a 2, that's a 4. So we've either got 2 and 4 here, or we've got 3 and 6, and then we won't know the order. So what does that mean? Well, no, yeah. Okay, I want to come back to this box again and ask where 3 is in the box, because 3 now it can't be on an X because of the 7 being in the 12 cage. It can't be in that cell, so it's in one of those 2 cells, which means it's not here. And if 3 isn't there, then 6 isn't here. Oh, this is so close to being... Hang on, where does that digit now go in box 7? Ah, yeah, this is it. Right. Where does this digit, this 4 or 6, has to find a home in this box? Now, if it's 4, it's very clear it's on an X. If it's 6, it's also on an X. It's slightly harder to see. But if it's 6, this has to be 9, because it can't be 6 and 6 there. So there is always, this digit is always on an X down here. And this is gorgeous with this square, because that means this digit can't be in there, that domino, because it will clash. It will create a 4-6 pair, and that will have no value. So this is a 4-6 pair, and that means this is a 2-8 pair, and that means this is a 9, because that's the only place 9 can go. And now that means this is 3-6. That's the only way that can go. That becomes 8. That becomes 6 now, because we know that this one was 2 greater than this one. So we've got 6 and 8 on this diagonal now, which means that those 2 squares are a 6-8 pair using the quadruple clue, which means 7 is in one of... Oh, which means we can place 7 in box 1. There's a 7 here, so that's a 7. You can't put 7 into those squares, or 8. So this quadruple clue now has a 7-8 pair into those 2 positions. This is mental. And now we've got... Oh, this is lovely. And we've got a 7 here on the 2-4-9 quadruple. So that 7 is not the same digit as a 2-4 or a 9. So those squares are 2, 4 and 9. So where does 5 go in this box now? There's a 5 here looking at those squares. 5 can only go in that cell. That must be 1 or 3. 5 is looking at the 12 cage, so that becomes 4 or 8, which fixes this square as a 6. That square is an 8. That's an 8. That's a 2. This is a 7-8 pair, so there must be a 2 in one of those 2 positions. Oh, and this can't be a 9 because it sees 9 on the diagonal. So this is 2 or 4. And if it's 4, this would be a 2. And if it's 2, this could be anything. Sorry, I'm not sure if I can resolve that. There might be a way. Do I now know what this is? And the answer seems to be no, which is weird. I know there's a 2 in... this is in... No, this is lovely again. This 2 in box 8 must be in that domino. And therefore, it can't be here. That can't be a 2 anymore. It would repeat in this, in the funny cage. So that's not 2, which means this is a 2, which doesn't do anything. Well, there's a 3 in one of those 2 squares by Sudoku. Oh, bother. Come on, Simon. Use your brain. It must be nearly done. What about this X. Do we now know what this is? Because it's not 4, 6 and it's not 2, 8. So it's an odd total. So it's odd, and if it's a 7, I've got to put the 7 at the top. So it's 7, 3. Is that possible? It might be. Or either that or it's 1 and 9. So these squares are relatively restricted. But maybe not in a way, not in enough of a way that it's useful. Those cells are a 1. Ah, yeah, okay, look at box, yeah, 7. That's a 1, 3 pair, which means that's a 4 now, which gives us a 4 and an 8 at the top of the grid. 4 is now removed as a possibility from this white dot, so 5 is removed as well, because 5 would need to connect to 4. So 9 comes out of here, and 7, which would need a 3, 4 pair. Whoa, hang on. A 7. Ah, everything's going wrong. 7 comes out of there. That's never been able to be a 4. It's got to be odd. So this is either 1, 2, or it's 2, 3. So there is always a 2 on this. Now that means that dot. Yeah, here we go. This dot. What is the nature of this black dot? It's not got 2 on it, so it's not 1, 2, it's not 2, 4, and it can't be 4, 8 because there's a 4 already in the cage. So that is a 3, 6 pair. I don't think I can disambiguate the order, but that does take 3 off this dot. So that dot becomes a 1, 2 pair, which means that square becomes a 3, which means this square, these two squares become a 1, 9 pair. And that 3 is helpful. That gets me a 3 and a 1. Probably does some other things as well, but I can't see what those are. So 1s and 9s and 2s and 6s. Ah, that's it's so weird. The digits I've got in that column are the exact digits I've locked into box 6, so I don't get any extra information from that at all. So this domino is either 4, 5 or 7, 8, but both of those things are possible. So if it's 4, 5, it has to be like that, and if it's 7, 8, I think it's got all the options in the world, although, no, oh, it can't be 7, the 8's up there, okay, so that square is 5 or 7 then, so it's odd, so this must be even. Oh, we've got a 5, 7 pair, look at that, we've got a 5, 7 pair in this funny cage. So the digits we've not put in the cage are 1s, 2s and 8s. So that's a 1. It sees 2 and 8. Good grief, that's a 1. This is a 2, 8 pair. The 1 gives us a 1, 2 pair up there. 2 must live in one of those two squares. Come on, keep giving up your secrets to us. 3, 5s and 7s into... so that's a 5 or a 7. Along row 8, and this is 3s, 5s or 7s, about which we know very little. Okay, alright, but that definitely felt like progress. Now I am going for my next trick to divulge the cell. No, I've no idea what I'm going to do next. I can't find anything to. I've got a 6 here, so that's a 6 and that's a 4. So this is not a 4, that's a 2 or a 9. Oh, and there's a 9 here. So 9 in this box goes here, so we can do more Sudoku. Of course I shouldn't be surprised that Sudoku is where we're lacking. Okay. Still don't see how to do that. What's about that white dot at the top? We've got 1s, 2s. Yeah, look at this. This row needs 1s, 2s, 7s and 9s in it. Well, the only consecutive digits are 1s and 2s, so that's a 1, 2 pair. That's a 9 and that's a 1. Still doesn't quite seem to do enough for me though. 9 is in one of those two cells. What about this diagonal? We've got loads of high digits on it. And the low digits we're missing are 1s, 2s, 4. Oh yeah, hang on, I've just noticed an interesting cell. 1s, 2s, 4s and 5s. This 1, 2 pair sees that one. Ah, that's so clever. Okay, this digit is not in that quadruple. Whether it's 4 or 5, it doesn't appear in the 2, 7, 8 circle. So this digit must be in the quadruple, so it cannot be a 4, and that disambiguates it. That's gorgeous. That is gorgeous. That 2 is useful. Gives me a 2 over here. There's probably more we can do with this, but I can't see how to do it, unsurprisingly. So this is a 1, 4, 5. 5 can never go on a black dot. Let's get rid of that. So this is 1 or 4. It's not 1 because it's on two Kropki dots. If you put 1 there, you've got to put double 2 into those squares. So that's a 4, that's a 5, that's a 1. This square is consecutive with 4 but isn't 5, so that's 3. And this square is either 2 or 8. And unbelievably, it looks like those are both possible. No, come on, that's rotten. That's really mean. 3 I can place in this box by Sudoku there. That gives me a 3 and a 1. 1, it goes here by Sudoku. Okay, so this column needs a 7 and an 8 to finish it. This column needs 2 and 5, I think, which doesn't seem to be resolved. I have a feeling I'm missing all sorts of things here, but never mind. Let us continue. 6 must be in this domino. And these 3 squares, maybe this is where we're missing a point, of 4s, 6s and 9s. And that can't be 9. And that can't be 4. Or, oh, actually that one sees 6 as well. So that's a 9. 6 here means that square's a 4, that square's a 6. Okay, that's something. Yes, 4 by Sudoku has to go in that cell exactly. And that means this is a 5, which is in the box, so that becomes a 7. That gets me the 7 and the 5 over here. That gets me this square as a 5 by Sudoku, so this becomes a 3, 7 pair. These 2 squares have got to be 7 and 8. Oh, come on, give up. You must be about to crack, you rotten thing. This 5 gives me a 2 over here, 2, 5 here. So this is 7 or 8. That gives me a weird triple or pair in this column. Oh, and I've got a 7, 8 pair in this row as well. So that means these 2 squares are a 6, 9 pair. So that's 9, that's 9, that's 6. So 6 is in one of these 2 cells. This square's 2, 7 or 8. And I suppose it sees the 7, 8 pair. So that must be 2, that must be 8. That must be 7, that must be 8, that must be 7, that must be 8, that must be 7. Good. Okay. Now, where shall we look next? Let us have a look down this column. That's a 1, that's a 2, that's an 8 now. So we have got a 2, a 7 and an 8 around this quadruple clue. What about that white dot domino? No, that's a totally useless domino. It's got too many options still. This column, though, needs a digit in it, doesn't it? It needs a 4 at the bottom. So these squares must include a 1, which we can place, and a 5, which we can place. So this is a 5, 6 pair. That suggests this should be done, and indeed it is. These squares have got to be 3, 4 and 7. So that's a 3, that's a 7, that's a 4, that's on a dot, which must now be a 5. And that we must have to put 7 and 6 into these. So the 7 goes here, the 6 goes here, the 6 and the 3 get unwound, the 3 and the 7 get unwound, and finally the 6 and the 5 get unwound, and we have finished the puzzle. Yes, that's brilliant. That really is brilliant. That was not easy either. That was a lot harder than I was expecting. I think I saw all of the clues and thought, well, this must be easier than a normal puzzle. But it wasn't at all. I couldn't see what to do for ages. I mean, the set idea is very lovely, but not straightforward to see, at least not for me. And even once you get that, you have to do quite a lot of thinking about how this can be unwound uniquely using these lovely quadruple clues in box 1. Really beautiful, and the way that you could eventually work out how these X dominoes work down here as well, that was quality. It's a quality puzzle. There's so much cunning that's gone into it. I'm slightly worried I've missed an easier way into that. As I say, there seems to be a lot of information for the way I had to do it, but maybe Marvin, if you've watched the video, you might drop a comment in and let us know. But thanks so much for watching, and we'll be back later with another edition of Cracking the Cryptic.